Chapter 1. Stoichiometry. Chemical reactions take place according to certain laws. These laws are called the laws of chemical combination. These are no longer useful in chemical calculations now, but gives an idea of earlier methods of analyzing and relating compounds by mass. Law of conservation of mass, Lavoisier, 1774. During any physical or chemical change, the sum of masses of all substances present in reaction's vessel remain conserved. Law of constant composition or definite proportions, Proust, 1799. In a given chemical compound, the elements are always combined in the same proportions by mass. Law of multiple proportions, Dalton, 1803. Whenever two elements form more than one compound, the different masses of one element that combine with the same mass of the other element are in the ratio of small whole numbers. Law of reciprocal proportions, Richter, 1792. When two elements combine separately with a fixed mass of a third element, then the ratio of their masses in which they do so is either same or some whole number multiple. Gay-Lussac's law of combining volumes. According to Gay-Lussac's law of combining volume, when gases react together, they always do so in volumes which bear a simple ratio to one another. If these are also gases, provided all measurements of volumes are done under similar conditions of temperature and pressure. Avogadro's law states the volume of a gas at fixed pressure and temperature is proportional to the number of moles or molecules of gas present. Mathematically, we can write V is proportional to N. Or equal volumes of all gases under similar conditions of temperature and pressure contain equal number of molecules. Matter consists of tiny particles called atoms. Atoms are indestructible. In chemical reactions, the atoms rearrange, but they do not themselves break apart. In any sample of a pure element, all the atoms are identical in mass and other properties. The atoms of different elements differ in mass and other properties. When atoms of different elements combine to form compounds, new and more complex particles form. However, in a given compound, the constituent atoms are always present in the same fixed numerical ratio. Modern atomic theory shows that an atom is no longer considered to be indivisible. An atom has a complex structure and is composed of subatomic particles such as electrons, protons, and neutrons. Atoms of the same element may not be similar in all respects. Example, isotopes 2311 sodium, 2411 sodium. Atoms of different elements may be similar in one or more respects. Example, isobars 4020 calcium, 4018 argon. An atom is the smallest unit which takes part in chemical reactions. Although an atom is composed of subatomic particles, it is the smallest particle which takes part in chemical reactions. The ratio in which atoms unite may be fixed and integral, but may not be simple. For example, in a sugar molecule C12H22O11, the ratio of carbon, hydrogen, and oxygen atoms is 12:22:11, which is not simple. Dalton's atomic theory explains fundamental ideas about matter. Matter consists of tiny particles called atoms. Atoms are indestructible. They rearrange during chemical reactions. In a pure element, all atoms are identical in mass and properties. Atoms of different elements differ in mass and properties. Combining different elements form new compounds with fixed ratios. Modern atomic theory states atoms are no longer indivisible. An atom has a complex structure composed of subatomic particles. Atoms of the same element may not be similar in all respects, like isotopes. Different elements may share similarities. These are known as isobars. Atoms are the smallest units participating in chemical reactions. Chemical ratios may be fixed and integral, but not necessarily simple. Atoms of one element can be changed into atoms of other element. Example, artificial nuclear reactions. The mass of atom can be changed into energy according to Einstein's equation. E is mc square. E is energy, m is mass, c is the velocity of light. Mass and energy are interconvertible. Definition of 1 mole. A collection of that many entities as there are atoms in 12 grams of carbon-12 isotope. 1 U is 1 AMU, 1 upon 12 of the mass of one atom of carbon-12. 1 gram upon Na is 1.66 into 10 raised to power minus 24 gram. For elements, 1 gram atom is 1 mole of atoms is Na atoms. Gram atomic mass, or GAM, is the mass of Na atoms in gram. Mole of atoms is mass in gram upon gam or molar mass. For molecules, 1 gram molecule is 1 mole of molecule is Na molecule. Gram molecular mass, GMM, is the mass of Na molecule in gram. Mole of molecule is mass in gram upon GMM, or molar mass. For ionic compounds, 1 gram formula unit is 1 mole of formula unit is Na formula unit. Gram formula mass, GFM, is the mass of Na formula unit in gram. Mole of formula unit is mass in gram upon GFM or molar mass. 1 mole of a substance contains 6.022 times 10 to the 23 particles. It weighs as much as molecular weight or atomic ionic weight in grams. If it is a gas, 1 mole occupies a volume of 22.4 litres at 1 atmosphere and 273 Kelvin. Average or mean atomic mass is calculated using A1 times X1 plus A2 times X2 and so on, upon X1 plus X2 and so on. Here, A1, A2 are isotopic mass of element, and X1, X2 are natural abundance of isotopes. Average or mean molar mass is M average is M1 times N1 plus M2 times N2 and so on upon N1 plus N2 and so on. Here, M1, M2 are molar mass of substances and N1, N2 are mole of substances present in the container. Empirical formula shows constituent atoms in simplest ratio. Molecular formula depicts actual number of atoms in a molecule. Relation between molecular and empirical formula is molecular mass upon empirical formula mass. Density is mass divided by volume, measured in grams per cubic centimeter. Relative density is density of substance divided by density of reference substance. Specific gravity compares density of a substance to water at 4 degrees Celsius. Vapor density is the ratio of density of vapor to density of hydrogen. Vapor density equals density of vapor divided by density of H2 at same conditions. Vapor density also equals molecular mass divided by 2. Stoichiometry, pronounced stoichiometry, is the calculations of the quantities of reactants and products involved in a chemical reaction. Following methods can be used for solving problems. A. Mole method. Balancing is required. For example, 2KClO3 equals 2KCl plus 3O2. Mole of KClO3 over 2 equals mole of KCl over 2 equals mole of O2 over 3. B. Principle of atom conservation. POAC. Method. Balancing is not required. For example, KClO3 turns by KCl plus O2. POAC for K. 1 times mole of KClO3 equals 1 times mole of KCl. POAC for Cl. 1 times mole of KClO3 equals 1 times mole of KCl. POAC for O. 3 times mole of KClO3 equals 2 times mole of O2. Concept of limiting reagent. A. Limiting reagent. It is very important concept in chemical calculation. It refers to reactant which is present in minimum stoichiometry quantity for a chemical reaction. It is reactant consumed fully in a chemical reaction. So all calculations related to various products or in sequence of reactions are made on the basis of limiting reagent. B. Calculation of limiting reagent. Divide given moles of each reactant by their stoichiometric coefficient. The one with least ratio is limiting reagent. Percentage yield. The percentage yield of product equals actual yield times theoretical maximum yield times 100. Concentration terms. A. For solutions, homogeneous mixture. If the mixture is not homogeneous, then none of them is applicable. E. Percent by mass, weight by weight, equals weight of solute over weight of solution times 100. I% by mass means 100 grams solution contains X grams solute, therefore I% minus X solvent. Percentage with PV equals the weight of solute over the volume of solution times 100. X% with V means 100 milliliters solution contains X gram solute. Stoichiometry, pronounced stoichiometry, is the calculations of the quantities of reactants and products. Following methods can be used for solving problems. A. Mole method. Balancing is required. For example, 2 KClO3 times 2 KCl plus 3 O2. Mole of KClO3 divided by 2 equals mole of KCl divided by 2 equals mole of O2 divided by 3. B. Principle of atom conservation. POAC. Method. Balancing is not required. POAC for K. 1 times mole of KClO3 equals 1 times mole of KCl. POAC for Cl. 1 times mole of KClO3 equals 1 times mole of KCl. POAC is hours equals 2 times mole of O2. Concept of limiting reagent is very important in chemical calculation. It refers to reactant which is present in minimum stoichiometry quantity for a chemical reaction. It is the reactant consumed fully in a chemical reaction. So all calculations related to various products are made on the basis of limiting reagent. Calculation of limiting reagent. Divide given moles of each reactant by their stoichiometric coefficient. The one with least ratio is limiting reagent. Percentage yield. The percentage yield of product equals actual yield divided by theoretical maximum yield times 100. For solutions. If the mixture is not homogeneous, then none of them is applicable. Percent by mass, W equals the weight of solute over the weight of solution times 100. X% by mass means 100 gram solution contains X gram solute. 100 minus X gram solvent. Percent WV equals weight of solute times volume of solution times 100. X% WV means 100 milliliter solution contains X gram solute. Percentage V over V equals volume of solute over volume of solution times 100. For gases, percentage by volume is same as mole percent. Mole percent equals moles of solute divided by total moles times 100. Mole fraction, X, equals moles of solute over total moles. Molarity, M, equals moles of solute divided by volume of solution in litre. Molality, M, equals moles of solute over mass of solvent in kilograms. Parts per million, ppm, equals mass of solute divided by mass of solvent times 10 to the 6th. Formality, F, equals know of formula unit divided by volume of solution in litre. On adding solvent in a solution, number of mole of solute remains constant. Minus F equals MIV. Mixing of two solutions of same solute, MFVF equals M1V1 plus S. Volume strength of H2O2. H2O2AQ, solution labeled as XV, means X volume of O2 at specific conditions. Molarity of H2O2 equals volume strength of H2O2 divided by 11.2. Stoichiometry, or gas analysis, involves calculations based on gaseous reactions. Gay-Lussac's law of volume combination holds good. Problem may be solved directly in terms of volume in place of mole. The volume of gases produced is often given by mentioning certain solvent which absorb gases. Solvent. Gases absorb KOH aqueous, CO2, SO2, Cl2, ammonium 2Cl2, CO, turpentine oil, O3, alkaline pyrogallol, O2, water, NH3, HCl, anhydrous CuSO4 plus CaCl2. Oxidation number. It is the charge, real or imaginary, which an atom appears to have when it is in combination. An element may have different values of oxidation number depending on the nature of the compound in which it is present. Oxidation is the addition of oxygen, removal of hydrogen, and loss of electrons. Reduction involves removal of oxygen, addition of hydrogen, and gain of electrons. A reaction in which oxidation and reduction occur simultaneously is called a redox reaction. Oxidizing agents are compounds that oxidize others and themselves are reduced. Reducing agents reduce others and themselves get oxidized. Balancing redox reactions can be done using the ion-electron method or the oxidation number method. Law of chemical equivalence states that equivalence of all reactants and products must be the same. 2A plus 3B equals 4C. Equivalence of A equals equivalence of B equals equivalence of C. Equivalent mass of A equals molar mass of A divided by valency factor. Equivalence of A equals weight of A in grams divided by equivalent weight of A. Number of equivalents of A equals number of moles of A times N factor. Normality, N, is defined as the number of equivalents of solute in 1 liter of solution. N equals number of equivalents of solute divided by the volume of the solution in liters. Also written as N equals Wg times 1000 divided by E times V, Fock, where W equals weight of solute, E equals equivalent weight, V equals volume of solution. N equals molarity times valence factor. Milliequivalents of solute equals N times V in mils equals M in mils times N factor. In case of non-redox reaction, N factor equals mole of charge displaced per mole of species. In case of redox reaction, N factor equals mole of electrons gained or lost per mole of species. Titration is a procedure for determining the concentration of a solution. Key terms: primary standard, standardization, standard solution, titrant, titrate. Types: non-redox reactions and redox reactions. These include acid-base titrations, double indicator acid-base titrations. Precipitation titration methods are essential in chemistry. Back titration is a common practice in quantitative analysis. Redox reactions include different types of titrations, such as iodometry and iodometry. In non-redox titrations, we focus on acid-base titrations to find unknown strengths. At equivalence points, we determine acid or base concentrations accurately. Using double indicators helps identify multiple endpoints in polyacidic titrations. For example, Na2CO3 reacts with HCl, revealing multiple endpoints. Phenolphthalein and methyl orange serve different pH ranges for effective titration. Dilution does not change the amount of substance measured, but can alter molar concentration. Precipitation titration helps determine salt solution strength through reaction with another reagent. At equivalence point, the milliequivalents of NaCl and AgNO3 must be equal. 2. Redox titrations. At equivalence point, milliequivalent of oxidizing agent used equals milliequivalent of reducing agent reacted. Subnotable: reagent, half reaction, N factor of reagent. 1. Fas more salt, FeSO4, NH42, SO4, 6H2O, E squared plus E minus. Q, MnO4K minus, permanganate ion, MnO4 minus plus 8H plus 5EO. 5. 3. MnO4 minus in basic medium, Mn7 plus E minus is equal to Mn6 plus 1. 4. MnO4 minus in mild basic or neutral medium, Mn7 plus E minus equals Mn4 plus. 3. 5. Cr2O7 cubed dichromate ion, Cr2O7 plus 14H plus 6E minus equals 2 Cr3 plus 7H2O. 6. C2O42 oxalate ion, C2O42 proton CO2 plus 2E minus. 2. 7. As2O3 OH2O 2ASO4 minus 10 H plus 4E minus. 4. 8. COCl2 bleaching powder, COCl2 plus H2O plus 2Ki equals COOH2 plus I2 plus 2KCl. 9. MnO plus 4HCl concentrate, MnCl plus Cl2 plus 2H2O. 10. IO3 minus. IO3 minus plus 5I plus equals 3I2 plus 3H2O. 5. 11. H2O2 act as oxidizing agent. H2O2 plus 2E minus equals 2H2O. 2. 12. H2O2 act as reducing agent. H2O2 equals O2 plus 2E minus. 2. 13. H2O2 disproportion. H2O2 equals H2O plus 1/2 O2. 14. Cl2 disproportion. 3Cl2 plus 6OH minus equals 3Cl2 plus 5Cl plus 4H2O. 15. H2S in acidic medium. H2S plus I2 equals S plus 2I minus plus 2H plus. 16. SN2 plus in acidic medium. SN2 plus I2 equals SN4 plus 2I minus. 17. N2H4. N2H4 remains N2 plus 4H plus 4Es. 4. 18. SO3 2 minus in acidic medium. SO3 2 minus plus H2O. SO4 2 minus plus 2Es plus 2H plus. 2. 19. Na2S2O3 sodium thiosulfate or hypo. 2Na2S2O3 plus I2 2NaI 1. I2 plus 2E minus equals 2I minus. 2. Iodimetry titration. In such titrations, iodine solution is used as an oxidant. Iodine is directly titrated against a reducing agent. This type of titrations are used for the determination of strength of reducing agents like sulfides, arsenides, thiosulfates, etc. by titrating them against the This type of titration involves free iodine. Here, iodine's solution is treated with known sodium thiosulfate solution. I2 plus 2Na2S2O3 equals 2NaI plus Na2S4O6. Equivalence of I2 equals equivalence of Na2S2O3 used. Iodometry titration is an indirect method of estimation of iodine. An oxidizing agent is used to liberate from iodine solution, and the liberated iodine is treated with a standard solution of a reducing agent from a burette. A neutral or an acidic solution of an oxidizing agent is used, and the amount of liberated I2 is equal to the equivalence of this oxidizing agent. These titrations are used to determine the concentration of K2Cr2O7, KMnO4, CuSO4, ferric ions, H2O2, etc. These titrations are carried out in following 2 steps. Step 1. Oxidizing agent, X, plus Ki, excess, equals I2 plus reduced state of oxidant. Step 2. Liberated I2 plus 2Na2S2O3 to NaI plus Na2S4O6. Back titration is used in volumetric analysis to find out excess of reagent added by titrating it with suitable reagent. It is also used to find out the percentage purity of a sample. For example, in acid-base titration, suppose we have added excess base in acid solution. To find excess base, it is back titrated with another acid of known strength. Equivalent of base equals equivalent of acid solution. Hardness of water. Definition of hard water. Hard water has soluble salts of calcium and magnesium ions. Degree of hardness defined as number of parts by mass of CaCO3 present in million parts of mass of water.